NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hello, everyone, and thank you for coming to JPL for this Von Karman lecture on this very chilly November evening. You're here tonight to learn about our Juno mission to Jupiter. Juno launched in August of 2011 and will arrive at Jupiter on July 4th, right? July 4th, Independence Day, 2016. Jupiter is by far the largest planet in our solar system. It has more than twice the mass of all the other planets combined. It almost certainly was the very first planet to form, and understanding its formation is a key to understanding our very own solar system. So tonight's guest is the project scientist for the Juno mission. He's Steve Levin. He received his PhD in physics from the University of California, Berkeley in 1987, where he then worked as a postdoctoral researcher and research physicist until 1990, which is when he came to JPL. His research interests have included measurements of the cosmic microwave background radiation, the search for extraterrestrial intelligence, measurements of magnetic fields in star-forming regions, and modeling of the inner Jovian radiation belts. He has done radio astronomy with instruments on mountaintops, at the South Pole, on large radio telescopes, on high-altitude balloons, and on spacecraft. He has published dozens of papers and won numerous awards, including a NASA Exceptional Achievement Medal in 2012. He literally, I have to tell you this, he literally jumped on a plane and flew home last night just to be here. He flew home from a science meeting in Maryland. So please join me in giving Steve Levin a very warm welcome.
Thank you. Is the mic working? Well, let's see if we, now it's working. Terrific, thank you. Okay, so after that introduction, I feel like it must be important or something. I'm gonna tell you about Juno, which is on its way to Jupiter, and as you just heard, gets there on the 4th of July. Actually, we cheated a little. It really gets there on the 5th of July Universal Time. That's how we usually count things, is Greenwich, England. But here in California, it's gonna be 4th of July in the evening. So fireworks from the spacecraft at the same time we have fireworks here in California. So we couldn't pass that up. It's gotta be called 4th of July. All right, well, what is Juno? What are we doing here? The Juno spacecraft, first of all, it's the first solar-powered mission to Jupiter, first solar-powered spacecraft to go out that far. We have a bunch of science instruments on it, depending on how you count things. It's 8 or 9 or even 10 instruments, as you'll see. There's a lot. I'm not going to read this whole thing. I'll tell you about what we're going to measure in a little while. But it's a spinning polar orbiter that we launched on August 5th, 2011. And it takes 5 years to get to Jupiter, but it's finally getting there. We're going to learn a lot about Jupiter, and that will teach us a lot about the solar system and how planets form and things like that. I see I have a typo here. It's actually a 14-day orbit, and we'll talk about that in a little bit. It's in NASA's New Frontiers program. You can read the science objectives, and I'm going to talk a lot about them too, so I won't read that. I'm going to try to rush through the slides so we can get to questions, because questions are the most fun part. But I do have to mention that this is a PI-led mission. That is, there's a principal investigator, Scott Bolton, who's in charge of the entire thing, and then delegates that authority, some of that authority, to a project manager and a project scientist and a whole team of people here at JPL and at a number of institutions around the world. And at the time this was selected, it was the largest PI-led mission NASA had ever done. Usually if things are big enough, it's sort of run by committee. And in our case, at least, I think it worked out really well that they chose to do it that way. We've got an efficient team, and we're really working well together. So I'm really pleased NASA chose to do it that way. Okay, so how do we get there? That's usually the place to start. Well, to begin with, we launched the spacecraft without enough energy to get to Jupiter. That's because we didn't have a big enough rocket to get it moving so fast that you could go direct to Jupiter. So the idea is we launched it from the Earth. We took advantage of everything we could with the Earth's spin and motion and the spacecraft and the rocket and all of that stuff. And that put it in an orbit around the sun that went out somewhere past the orbit of Mars. And then when we're out there, we fired the main engine actually twice to aim so that we came all the way back to Earth. And the reason for doing that, which we did in October of 2013, was to use the Earth's gravity as a slingshot and get an extra boost, and that finally gave us enough energy to go all the way out to Jupiter. So we're in that final coasting phase now, and we'll get to Jupiter on the 4th of July, and then the thing to do is fire the main engine and slow down so we don't blow on past. So that's probably the scariest time of the whole mission, because you have to make the main engine work, you have to make the spacecraft fire the main engine at the right time so that you slow down and orbit Jupiter. Doesn't help to get it all figured out and have a problem and solve the problem and fire the main engine half an hour later, because by that time it's too late and you don't get into orbit. So that's why it's a critical event, and we'll be biting our nails a little bit on the 4th of July, although cross your fingers, I'm sure everything will work great. All right, well, by now you should be asking yourself, why are we doing this? And the answer is that even though Jupiter is the largest planet in the solar system by far, twice as big as all the others, twice as much mass, and even though we've been studying it literally for hundreds of years, it's one of the very first things anybody ever looked at in the sky with a telescope. And even though you can see it from the Earth, and we've had a spacecraft there, more than one spacecraft has gone by, and Galileo spent a long time in the Jovian system, there are still an amazing number of basic questions that we don't have answered about Jupiter. And that's because it's hard. When you look at Jupiter, mostly what you're seeing is the very tops of the clouds in Jupiter's enormous atmosphere. So we have basic questions like, how did Jupiter form? What's its composition? What's it made out of? We know it's mostly hydrogen and helium, but the very next element that's the third most common element in the solar system is oxygen. We don't know how much oxygen there is in Jupiter. We think there's a solid core, or at least a dense core, down in the center there, somewhere between 3 and 20 times the mass of the Earth, but we have no direct evidence that it even exists, let alone how big it is. We see a giant aurora in Jupiter's upper atmosphere in the north and south poles, northern and southern lights, like the aurora here on the Earth, only enormously bigger. We don't really understand exactly how that works and the mechanisms that power them. We know the general idea. Jupiter has an enormous magnetic field, the strongest magnetic field by far of any planet in the solar system, and we think actually that magnetic field comes from an ocean of liquid metallic hydrogen deep inside the planet. But the details of how you form that magnetic field, or in fact, how you form a planetary magnetic field, are still a bit of a mystery. We hope to solve those mysteries. We hope to be able to answer those questions. That's why we're sending a spacecraft. So what do we know? Well, we know, for example, that Jupiter's hotter on the inside than the outside, and that's because it's still cooling off 4.5 billion years after it formed. That's how big it is. We know something about the temperature profile of the atmosphere, how it cools off, and that'll become important later, as you'll see, because we're going to use that to help us learn how much water there is, which tells us the oxygen content. We're pretty sure that deep inside there's this ocean of metallic hydrogen. And you know, I talk about Juno and Jupiter a lot. I use that phrase all the time, liquid metallic hydrogen. But each time I want to stop and get you to think about all three words: liquid, metallic, hydrogen. So hydrogen is the lightest element there is. If I filled a balloon here on Earth with it, it would float up into the sky. On Jupiter, the conditions are so intense, the pressure is so high from Jupiter's enormous gravity, that not only has that hydrogen gas been squeezed down into a liquid, it's squeezed so much the electrons are coming right off the atoms. It conducts electricity. It's a metal. It's the swirling motion of that liquid metallic hydrogen that we think generates Jupiter's enormous magnetic field. Down underneath that, we think there should be a dense core in the center of Jupiter. There's no way we can get anywhere close enough to directly sample that core or even the metallic hydrogen layer, which is at a couple million times the pressure here on the Earth. So we need to figure out a way to measure it indirectly. That was the puzzle for Juno. That's what we tried to do, is come up with a way to learn about the interior of Jupiter without going inside it. I should mention as well, of course, there's weather. That's what you see on Jupiter. You see the upper atmosphere, you see clouds and streams and things moving and so forth. And we want to penetrate below that weather. At least we want to study what's below the weather. Okay, so one of the key puzzles about Jupiter is when the Galileo spacecraft dropped a probe into Jupiter. We dropped a probe into one spot on Jupiter in the 1990s. Measured a lot of things. We learned a lot from Galileo, and we learned a lot from the probe. But one of the things we found was a real puzzle that nobody had anticipated. And that is, if you take the heavier elements in Jupiter and you measure how much of them there are, and you compare the ratio of the heavier stuff to hydrogen, which is most of the planet, and you take that ratio and compare it to the sun, what people originally thought was, well, if Jupiter formed all at once from the same cloud of gas and dust that made the sun, then the proportion of all the elements should be about the same. So if I took the ratio of, say, argon to hydrogen, I should find about the same ratio in Jupiter as I find in the sun, or krypton or xenon or carbon or all the other elements that I've got here on the chart. These are things measured by the Galileo probe, and what they found was actually they were enriched. It was 2 or 3 times as much of the heavier elements as one would expect. So that was a puzzle. How the heck did that happen? And then water, they found almost none. So ultimately, after puzzling over this for a while and coming up with various theories and explanations and so forth, the conclusion that most people agreed on is that for the water, we didn't get the global water abundance. We were measuring in one spot, and we thought that when the probe went in to beyond 20 bars, 20 times the pressure here on the Earth, that would be deep enough for where the water was well mixed. But we must have been wrong. There was other evidence for that. The value was still changing as the probe went in. So we just got unlucky, and it went into a dry spot, went into the Sahara Desert on Jupiter, and therefore we saw hardly any water, but that doesn't represent the global abundance of water on Jupiter. Okay? We don't know for sure if that's true, but that's the explanation that we're going with at the moment, because otherwise nobody knows why there'd be so little water. And it's at least a plausible explanation, but it's one of the reasons Juno wants to measure it a different way. And then the rest of these, well, the leading theory for how you get that enrichment is instead of forming all at once from the same cloud of gas and dust that forms the sun, imagine that what happened is asteroid-sized objects, mostly out of ice, because that's what would be there that could be a solid, started to form. And in the early solar system, before we had planets, those icy planetesimals stuck together. They crashed into each other, and big pieces of them stuck, and you wound up with a planet that grew first from icy planetesimals until it had enough mass to have enough gravity to gather in the hydrogen and helium. So that would explain the enrichment of the heavier elements, but it would predict you should find a lot of water too. And it leaves water as a key to how it formed. Because if it formed close to the sun where it's warm, you get a different amount of water than if it formed far from the sun where it's cold. If the water carried the other stuff in with it, how much it could carry depends on the temperature. Things that are really cold are going to stick to the water better than things that aren't. Okay, so it left us with the key puzzle, what's the water? And left us with a mission, with a spacecraft on its way to Jupiter to try to answer that fundamental question of how did Jupiter form? Which, remember, is a key not just to how Jupiter formed, but because Jupiter's the largest and because it formed first, it's also a key to how did the other planets form? How do solar systems form? Where do we come from kind of questions. All right. Well, I promised to rush through and get to where we could answer questions, and now I'm going to spend about eight hours on this slide. But that's because it covers more or less the whole mission. So what you see here on the left are the 4 big questions we're trying to answer. Now, obviously, any space mission, you're answering lots of different questions. You're after a lot of science, but these are the 4 big themes. The first one is origins. We want to understand how do planets form, how do solar systems form. And the key to that, the most important single number we're going to measure, probably, is the global abundance of water. How much water is there in Jupiter? Not for the usual reasons. You've heard of looking for water on Mars or looking at water on Europa because we're interested in life. In the case of Jupiter, it's only indirectly related to life. What we're really interested in the water content for is that's going to tell us about how did Jupiter form. And we want to find out if there's a dense core down in there. How big that core is, assuming that it's there, tells you about how many heavy elements came in and how things were put together. So it's another clue to the origin. In general, we want to understand the interior of Jupiter. When we look at Jupiter, we're seeing this enormous atmosphere, right? 300 times the mass of the Earth. A planet so big you could fit over 1,000 Earths inside it. And what we're seeing is the very, very tops of the clouds floating in the atmosphere. A tiny thin layer of Jupiter is what we can actually see. We want to understand all the other stuff underneath it. What's inside there? What's the interior made out of? So we're going to do that by measuring gravity from Jupiter and the magnetic field from Jupiter. And we're going to look at the water by measuring both of those and the radio waves that come out of Jupiter. So I've got color coding over here, if you can see it. All of these will affect many of the questions, but primarily, if you want to know about the origin, look for the green dots over here and which instruments will measure that, and the blue for the interior and so forth. We want to understand the atmosphere. The planet's mostly atmosphere from what we can see. And the part that we see at the top, we want to understand about the atmospheric composition. We want to understand the dynamics, how deep all those things go. We see, the Great Red Spot is a storm bigger than the entire Earth that's been around for hundreds of years. We have an idea what powers that. It's powered by the heat leaking out from inside Jupiter. But we want to know how deep does that go? How does that mechanism work? We see these belts and zones, jet streams moving at hundreds of miles an hour around the planet in different directions. What drives that? How does that become the Jupiter that we see? All of that is tied up in this question of the atmosphere and the dynamics. And then finally, Jupiter has this huge magnetic field, and it's got a magnetosphere that stretches so big that if you could see it, if it was visible from the Earth, it would be bigger than the full moon. This enormous magnetic field around Jupiter traps particles. It has this rapidly rotating planet. Think about that, actually. Jupiter is 300 times the mass of the Earth, more than 1,000 times the volume. It rotates every 10 hours. It's spinning more than twice as fast as the Earth. Well, that magnetosphere is this magnetic field spinning around, and it has to tie up with the solar wind and the magnetic field from the sun. So if you get far from Jupiter, it's got to match up to a magnetic field that's not rotating. Close to the planet, the magnetic field's rotating like crazy. Far from the planet, it's not. Somewhere in between, the clutch has to slip, right? And we think that's actually what drives the aurora. So you see these northern and southern lights that are from electrons streaming down the magnetic field lines, ions, crashing into the upper atmosphere and glowing when it hits the atmosphere. That's the northern lights or the southern lights. We want to understand the mechanism that makes that work. How does this whole magnetosphere work? And so that's another central area of what we're trying to study. Now, as it turns out, we're in a pretty good orbit to do that. I think there's an orbit drawn on here, but you probably can't see it. Can you see it in the audience? Can you see the line drawn around there? It's a thin line. But basically, our plan is the spacecraft's going to come in over the pole of Jupiter and around like that, a couple hours from pole to pole, and then 14 days out far from the planet, and then come around again every 2 weeks for about a year and a half. And one of the reasons we're doing that is Jupiter is surrounded by radiation belts. That magnetic field is trapping high-energy particles. There are high-energy electrons circling Jupiter in this big donut-shaped radiation belt, like the Van Allen belts here on the Earth, only much bigger, because Jupiter's much bigger and the magnetic field's much bigger. And those high-energy electrons are going to fry the electronics of a spacecraft if you fly it through them. So we need a way to avoid the radiation belts. Previous spacecraft that have gone by Jupiter have done the sensible thing. They've stayed way outside the radiation belts, far from the planet. Well, we're either braver or dumber. What we're doing with our spacecraft is we're going to fly it under the radiation belts, between that donut and the planet. So we come in over the pole of Jupiter. I guess if you can't see the line, I'll draw it with the arrow here. You come over the pole of Jupiter, duck down in here and thread the needle between the radiation belt and the planet, and then come out again. So our first orbit's coming in pretty much parallel like that. So we'll have a nice path over the pole, get a great view of the poles of Jupiter, which haven't been seen well, come in really close to the planet so we can measure the gravity and the magnetic field, and then zip out the other side, spend 2 weeks recovering, and do it all again. But the problem is Jupiter's not a perfect sphere. Remember, it's rotating every 10 hours. So it stretches out at the equator compared to the poles. It's flattened at the poles. And that means our orbit around Jupiter won't stay that way. What's called the line of Apsides, the line of the orbit, is going to shift. So by the end of the mission, it's down like this, passing partly through the radiation belts. So we're going to build up a radiation dose as we go along, and that's mostly what determines the lifetime of the mission. All right, I told you it'd take a long time on this slide. So we're going to measure the interior of Jupiter. How are we going to do that? Well, first of all, gravity comes from the entire planet, including the core, including the belts and zones, and so forth. So by measuring the speed of the spacecraft as it falls around the planet in an orbit, we'll be measuring the gravity from Jupiter and therefore measuring the interior. Second, remember the magnetic field, I said, comes from this ocean of liquid metallic hydrogen deep inside the planet. So if we measure the magnetic field, we're measuring the liquid metallic hydrogen. And then microwaves penetrate through the clouds. So we have a microwave receiver on board that's going to use the natural radio emission from Jupiter because it's hotter on the inside than the outside. It glows in the radio. We'll see that radio glow coming from the inside, and we'll use that to learn about the deep atmosphere. Then, as I mentioned, we have this interest in the magnetosphere. We have a whole suite of instruments on board the spacecraft whose job it is to measure the particles that hit the spacecraft, measure the plasma waves traveling through the magnetic field and the plasma in the magnetosphere, an ultraviolet spectrometer that'll take pictures of those aurora, an infrared camera to take pictures of the aurora and measure the spectra. That'll also help us with the atmosphere. And then finally, we have a visible camera on board, which actually it'll do some good science, but it's not there for science. It's an outreach camera. The reason we're carrying a camera to take great pictures of the pole is mostly for outreach and education so that the general public can have a hand in using that camera, and I'll talk about that at the end of the talk. All right, I'm finally off of this slide. All right, there's the spacecraft with the different instruments on it, just show you roughly where they are. These great big things are the solar panels to give you a sense of scale. Lots of different ways to do that, but the way I like to think of it is if you parked a 18-wheeler truck on the spacecraft, first of all, I'd kill you if you parked it on the spacecraft. But then the size of the container part of the truck would just about fit on one of those solar arrays, on one of those arms. That's the size of it. Another way to look at it is on a professional basketball court, you could just barely fit the spacecraft on the court. Okay, so that's the size. And then there's a magnetometer way out here on the boom at the far end of the spacecraft. Anybody know why I have the magnetometer way out at the end?
To be away from the mass of the thing.
To be away from the spacecraft, right. I want to measure the magnetic field of Jupiter, not the magnetic field of the spacecraft. So by having the magnetometer way out at the end, far from the spacecraft, and actually having two of them, because one's a little closer, you can do a comparison, and having a magnetically clean spacecraft, that is, keep the magnetic field from the spacecraft as low as we can make it, Put all of those together, and Jack Connerny, who's the PI for the magnetometer, can do an excellent job of measuring the magnetic field of Jupiter and not so much the magnetic field of the spacecraft. Although actually the truth is he can measure the spacecraft really well too. Okay, we have microwave radiometer, 6 different channels spread out around it. We use the main communication antenna to do the gravity science. I'll talk about that in a little while. And you can see the other instruments. I'm not going to go through them one by one because they're just lines on the chart at the moment. So instead, let's talk about the main experiments a little bit. So the first one we're going to talk about is the microwave radiometer, called MWR. And what we have is 6 microwave antennas distributed around the spacecraft. And in fact, the largest of those, the lowest frequency, this great big shining thing here, this antenna, pretty much determined the size of the spacecraft. When we were figuring out how big the spacecraft needs to be, basically the answer was so that one side is big enough to put this on it. But there's 5 other channels. So there's the largest channel at 600 megahertz, and then there's another channel at twice that frequency, so half the wavelength. It gets to be smaller. And then a panel on which we have the remaining A 3 through 5 channels, so channels 3 through 5 fit on the same panel, and a tiny little horn for the high frequency channel. And the way that they work is on these 2 sides, they look out away from the spacecraft, and the spacecraft spins this way like a top. So each channel gets its turn to sweep across the sky and sweep across Jupiter. And furthermore, if you put the spacecraft up here in our orbit and you think about what happens, if I pick a spot on Jupiter, I'm going to look at that spot from right above, but I'm also going to look at it later in the trajectory as we spin around from a different angle and from another angle. And earlier I looked at it from a shallow angle. So each spot on the planet I get to look at from a range of angles at 6 different channels. That's really helpful because not only am I doing a CAT scan by looking at all the different angles, but each of the 6 different channels penetrates a different depth into the atmosphere. And one of the main components that determines how deep it penetrates is water. So by measuring how deep they go into the atmosphere, we're effectively measuring how much water there is. Now remember I mentioned early that we had a temperature profile on Jupiter. We know something about the temperature profile. Well, the way the temperature varies depends on how much water is in the atmosphere and other things. So by measuring the radio waves, which are coming from the glow, so how hot it is tells you how much radio power you're going to get out. By measuring what we see in each of the 6 different channels at the whole range of angles, putting that together with the model of the atmosphere and how the temperature should vary depending on how much water there is, we can tease out how much ammonia and how much water and how much of other elements there are in the atmosphere of Jupiter to pull out the prize, which is the global water abundance of the planet. Now, we get down with our longest wavelength, our lowest frequency channel, penetrates down to some of the information it's getting coming from a pressure of 1,000 bars, 1,000 times the pressure here on the Earth, which sounds really great, but on the scale of Jupiter, that's pretty small. Nonetheless, we think it's way beneath the weather layer. We're beneath all the storms and stuff that we see and down to a layer where the water should be well mixed, so we'll be measuring the global water abundance. And of course, just in case we're wrong about that, we'll find out because unlike dropping a probe into one spot, we're going to look at a wide range of Jupiter. We'll be looking at lots of different places. So we'll know if we're not getting the same water number in all those different places that we're not seeing deep enough or we need to understand the picture better. Okay, just to make it a little harder, the reason you can't do that from the Earth is if you had radio eyes, this is what Jupiter would look like from the Earth. Those radiation belts I mentioned before with the high energy electrons, take electrons and you whiz them around in a magnetic field at close to the speed of light, they give off radio waves like crazy. So from the Earth, Jupiter glows in the radio, but it's the high energy electrons you see, and Jupiter behind it is pretty dim and hard to see. So you can't really do this measurement from the Earth. But from a spacecraft, remember I'm putting the spacecraft right there underneath the radiation belts. So when it's right here, the spacecraft can look at the planet, and the bright light from the radiation belts is shining over our shoulder instead of in our eyes. We still have to account for it and subtract out its contribution because some of it's going to leak in, but that's not as big a problem since the spacecraft is spinning and all of those 6 channels that we're looking at the planet every 30 seconds are looking out at the radiation belts. So we know we measure what we want to subtract, and then we measure the planet. We spin around again, we measure what we want to subtract, and measure the planet. All right, so that's the big picture view of the microwave radiometer. See, we're speeding up a little bit. Then the gravity measurement. Gravity is the largest instrument that's part of Mission Juno. And the reason I say that is the gravity instrument isn't on the spacecraft. It's only partly on the spacecraft. It's the link between the communications antennas on the spacecraft and the giant radio telescopes here on the Earth that make the gravity instrument. So in effect, it's an instrument that stretches from the Earth all the way to Jupiter. And the way that works is if you send a radio signal from here up to the spacecraft and the spacecraft turns around and sends it right back at the same frequency, the fact that the spacecraft is moving is going to shift the frequency of that radio signal. And it gives you a very precise measurement of exactly how fast the spacecraft is moving in a direction away from you or towards you. That's called the Doppler effect. And you hear the same thing every time you hear a police car or an ambulance with its siren on drive by. When the sound sounds different as it's coming towards you from when it's coming away from you. And that's because the sound waves are getting their frequency shifted as it comes towards you, and then they shift the other direction when it goes away. We use that same effect on the spacecraft to measure Juno's speed as it falls past Jupiter. We do that with a couple of radio instruments on the spacecraft that send a signal back. We have our main communication antenna and the X-band receiver at about 8 gigahertz that we use to communicate with the spacecraft. We can measure the Doppler from that, measure the speed. And we also have a Ka-band transceiver that takes that signal that comes up and turns around and bounces it back to the Earth that was built in Italy and contributed by the Italian Space Agency that will help us measure it more precisely because the higher frequency penetrates through the solar system better and doesn't get distorted the same way. Okay, so imagine the spacecraft now falling past the planet. If there's a core in there and the thing is spinning around every 10 hours, the core is going to stretch differently than the rest of the planet. So the spacecraft goes by and speeds up and slows down again. How much it speeds up and slows down will be different depending on whether there's a big core in the middle or no core or a smaller core. That's what the gravity does, and we combine it, of course, with the water measurement to fit together. We can also use it to look at atmospheric dynamics, and we can use the radio receivers to do that as well. So we see these belts and zones, and the movie here, you can see how they move relative to each other, and the giant storm, that great red spot there is bigger than the whole Earth. In that picture, it's about twice as big as the Earth, but if you took a picture today, it would be more like 1.5. It's been shrinking. It's been around for hundreds of years, and we're getting to see it shrink now. If we're lucky, you and I might be alive in time to see it disappear. It'd be really interesting. Anyway, those belts and zones are moving at high speed, so as the planet rotates around, if they've got a lot of mass and they're deep, or if they've got less mass and they're shallow, then they'll have a different gravitational signature. So as the spacecraft falls past them, it'll speed up and slow down as it falls over them in a different rate, different way, depending on how deep they go. So if you imagine, this is just an artist's conception, somebody just made this up, but imagine structures that go deep versus structures that don't go deep. You'll get a different gravity signature, and of course you get a different microwave signature as well, because remember that's coming from deep inside the atmosphere, and how much you see depends on what's in the way. So these structures will have some signature, and how deep it is, how it looks from different angles, will depend on how deep the structure is. All right, so we learned now we're putting the picture together, right? We're using microwaves to get the water and to get something about the atmospheric dynamics. We're using gravity to find out about the core and about the atmospheric dynamics. Then we're going to map Jupiter's magnetic field. And remember, that's generated in this liquid metallic hydrogen ocean down inside the planet, probably most of the planet. You go about a third of the way in, and you're getting to 2 million times the pressure up to where you can make liquid metallic hydrogen. So by mapping the magnetic field, since it's generated by the metallic hydrogen, we're learning about the motions of that and size of that ocean of liquid metallic hydrogen. And it's also a golden opportunity to learn about how planets make magnetic fields. Now, you might think that the place to learn about planetary dynamos, where a magnetic field comes from, is here on the Earth, because we can crawl around all over the Earth and measure the magnetic field to really, really, really high accuracy. But the problem is that the magnetic field on the Earth is generated by this molten iron down in the middle, and in between us and the core where it's generated, in between us and the dynamo, is magnetic material. So what we measure on the surface of the Earth is limited not by how well we can measure it, but by how well it represents the magnetic field that's generated down inside. On Jupiter, that's not a problem. It's hydrogen in between us and the dynamo region, and some helium. It's not magnetic. So if we measure the magnetic field surrounding the planet, we're measuring all the way down to the dynamo region. I don't know if you were all watching the movie instead of listening to me, I hope, and you saw the tracks go by. That's because as we orbit the planet every 2 weeks, spend that couple hours from pole to pole, Jupiter's spinning around every 10 hours. So we adjust the timing just a little as we go past the planet, and each time we can get a new longitude stripe. So we let it rotate around to where we want it and get another stripe past it. So the tour that we have set up, that's going to go into effect on the 4th of July, does 4 stripes so that you get a stripe every 90 degrees and get a sort of rough, very rough global picture of the planet, and then fill in, so now you have 8 longitudes and you have a better global view of the planet, and then fill in again to get 16, and then eventually you get 32. So by the time we're done, we'll have 32 longitudes evenly spaced around the planet, making a net like this where we've measured the magnetic field to learn about where it's generated deep inside. All right, so that teaches us about the core and about the composition, a lot of things, because it teaches us about the size of the dynamo region, how the dynamo works, and what those motions in there are. And then finally, the magnetosphere. Well, we're in just about a perfect orbit for studying the magnetosphere. Remember, we're coming in over the pole, and Jupiter, if you look at this picture in the lower right, Jupiter looks like this giant magnet. It's a picture of the Earth's magnetic field, only a lot bigger. So all of the magnetic field lines come out like this and around, and our trajectory takes us across every single field line and back out again. Right, so we come across all the different latitudes there are to come across, and that means you can be up here, measure the particles that are hitting the spacecraft, while you're using the ultraviolet and infrared cameras to look at the aurora down here and see what they're doing to the planet. So you get, this is an ultraviolet picture, you get some idea of what the aurora look like. You can see that's the footprint of Io. So picture volcanoes on Io spewing stuff out into space. The sun ionizes those particles. They track along magnetic field lines, and some of them wind up here on the planet making a glow. And by measuring that glow, that's one of the ways that we've figured out so far what the magnetic field looks like. We'll have a better measurement from Juno, of course. But now, if you're up there along that magnetic field line and you see the particles that are hitting the spacecraft, you know which particles, what kind of particles, what energies and so forth are getting down to the planet, and then you see the glow from the aurora. You're sort of in a perfect vantage point to understand how the aurora are formed. And if you want to study something else, say way out here in the magnetosphere, well, you're crossing those field lines too. So this is a great way, it's a great location for the fields and particles instruments. Okay, I'm almost ready for you guys to ask questions. Let me get down to the next one, which is, remember I promised to tell you more about the visible camera? So it's called JunoCam, and it will take great pictures of the poles of Jupiter. It's sort of designed that way to be able to get pictures of that polar region in the north and south where we don't have any good pictures. But it's also designed, and the way we're using it is designed, to do what we're calling science in a fishbowl. The basic idea is we want to do science out in the open with everybody who wants to participating and seeing what's going on and being part of it. So if you go to our Mission Juno website right now, one of the things there is this page for JunoCam that I'm showing you. And it has an opportunity for people to upload pictures of Jupiter taken from here on the Earth which will be used to make the map, because Jupiter changes, you need to get current pictures of Jupiter, to make the map that's used for people to look at the map and pick out spots and say, take a picture of this. This looks interesting. Take a picture of that. And then there'll be a discussion section where people can argue about it. And we will, the scientists, if a scientist wants us to take a picture of some particular object, go to the website, put it in, compete with Mrs. Field's third grade class to make a good case for it. And then there'll be a system of voting where the public can vote on which pictures should be taken. And we'll take that into account in choosing the pictures. So we hope to have a good scientific discussion about it, probably mixed in with comments like, that looks pretty, which is okay. We have a limited number of pictures we can take, and so we want to choose the best ones. And this is how scientists would normally do it, is have the debate over what's the best image, what's the best way to spend those bits, those communication capability. And the only difference here is everybody who wants to can participate in that same discussion. And then finally, when we take the pictures, we're going to take the raw data and put it out on the web. So there might be some professionals trying to process that data too, but anybody who wants to can take the raw data and turn it into pictures and show us what you got. So we already did that a little bit when we flew past the Earth and got some amazing things. Spacecraft flew past the Earth, JunoCam took some pictures. We weren't ready for all the planning and discussion and voting process yet, but putting the raw data out on the web was easy, so we did. And in less than 24 hours, we had some amazing pictures that people had just picked up the raw data and combined it and turned it into a picture. And it's not like taking the picture out of your cell phone and putting it up and you already have a good picture, because the way the camera works, it's got to take 3 different images to get red, green, blue, 3 different colors. We actually have a filter on there as well, a methane filter. So 4 images in different colors. And it's not take the whole image all at once. It's a scanning camera. So you take a little bar and you take into account the fact that the spacecraft is rotating and pull it out. And then you have to turn that into a picture. And you're going over Jupiter, or in the case of the Earth flyby, the Earth, which is a sphere, more or less. And so everything's distorted, and you have to put it all together, and you have to put those different colors together. And to me, it's absolutely flabbergasting that there are people out there who did all of that for fun. It's not their job, but they became experts on it because it's fun to learn about it, and they like to be part of it, and they were really excited to be part of the project. So we expect to have more people when there are pictures of Jupiter doing that. And who knows, maybe some of you guys in the audience will decide to go take a look and see what you can do. Okay, so I'm almost done, ready for questions. The last thing is Eyes on the Solar System. I hope a lot of you have heard of that already. It's NASA's 3D interactive way of finding out about the spacecraft that we have out there in the solar system. The website's up here. Juno's going to be part of it. There's lots of cool stuff about Juno you can find there. And we have 2 websites. We have the mission website, which is videos and movies and the JunoCam site and interviews with people on the project and all the cool project stuff that we could think of that we thought would be fun, and probably more to come. And we have the main NASA website, which has a section for Juno and, of course, links to each other. All right. Now, finally, we're ready for questions. I hope you have lots of questions, because that's my favorite part of any talk. And there's a microphone over there if anybody's ready. I don't know if there's a moderator or somebody, or I get to choose, but whoever's first in line, I guess. Go ahead.
Okay. So a 2-part question here. So what do you mean by recovering after Juno passes by the radiation belt? And do you predict that the radiation will decrease if the high-energy electrons disperse?
Okay. So let's do the first part of that first, I guess. What I mean by recovering after we get by the radiation belts is not so much the radiation, although it's possible that we'll have some problems, and we'll need to figure them out based on the radiation. But we think we've designed it all so that it can go through that gap between the radiation belts and the planet without having any major problems. However, we're going to collect a whole bunch of data right close to Jupiter. That's our main thing. We think of it as a flyby, as 32 flybys rather than orbits, because we're only spending a couple hours past Jupiter each time. So we collect all this data, then we have to send it back to the Earth. So we've spent a bunch of power, and remember we're solar powered at Jupiter, so our solar arrays develop around 500 watts at Jupiter. You have to run the whole spacecraft on about a third or a fourth of what it takes to run a hairdryer. Okay? So we're going to use all that power. We're going to drain the battery some when we're close to the planet. We're going to transmit to the ground, and that drains the battery. We need to recover. So we need to fill up the batteries, charge the battery again. So we need some time for that. We need to transmit all the data to the ground. So we need some time for that. And then the people on the ground need some time to process what the heck just happened and what did we learn, so that when we go around again, we're measuring what we want to measure. Now, I'm cheating a little bit because probably we won't make very many changes in the 14 days we'll have from one Para-Jove pass to the next, because it's too fast. By the time you get the data to the ground a few days later and you've figured out what you've seen and you said, hey, I want to measure something else, it's probably too late to safely send it up and measure it for the very next pass. But we have a process, and in 2 or 3 or 4 passes later, we can be making changes based on that. Or if something's really important, maybe we can do it right away. So all of that 2 weeks is what I meant by recover. Now, in terms of the radiation belts and the electrons dispersing, the electrons the high energy electrons are the most dangerous part of the radiation belt for us. So yes, if they were to disperse, then they would be less dangerous. But we have a pretty good idea of where they are. Not a perfect picture, but remember when I showed you the radio receiver, there was a radio picture of what Jupiter looks like in the radio, and we could see the radiation belts in the radio. It's complicated to go from what I see in the radio to what that means for high energy electrons, but we have a good enough picture that we have a pretty good idea of where they are, and we think we're safe where we're going, and of course we'll get great measurements when we're there. So thanks for the question. Oh, and that reminds me, actually, speaking of the radio, there's another project loosely associated with us called GAVRT, Goldstone Apple Valley Radio Telescope, in which school kids are using a radio telescope to collect radio data on Jupiter, and some of that data goes into the model to figure out where the radiation belts are. So we have school kids all over the country running a telescope over the internet, helping us with the radiation belt model.
Thank you.
All right, thanks.
Yeah, you mentioned that what we see of Jupiter isn't Jupiter, it's really just the aurora borealis and the radiation that goes around there. Did I misunderstand? And if I did misunderstand, how long have we known that? And if we know that now, when did we discover that? And then how do we project what the Jupiter actually looks like inside the part that we can't see
Okay.
up to this point?
So you're close, but what I'm saying is what we see at Jupiter is the tops of the clouds in the atmosphere. So when you look at this picture here, and I'll use the pointer to try and point at things, if you see the great red spot, that's a storm, it's huge, it's probably hundreds of miles deep, but that's nothing compared to the size of Jupiter, and it's clouds moving around in the upper atmosphere. Okay? When we see the aurora, which are in a different picture, I have them here, that one. So that's an ultraviolet image. It's not as easy to see them in regular visible light, although you can. You're seeing even higher in the atmosphere of Jupiter glowing in the ultraviolet. But we can see below that, below the aurora. We can actually see the upper atmosphere. What we can't do is see through the clouds to see what else is there. And we've known that for a long time now. I don't know exactly how long, but it's decades, maybe even 100 years.
Yeah. Okay, so if you look through a telescope, that's what you're actually seeing. You're not actually seeing the planet, you're just seeing
Well, you're seeing the atmosphere. The atmosphere is the planet. Remember, it's entirely possible that Jupiter doesn't have a core down in the middle. We think it should, but maybe the entire planet is atmosphere. That's a possibility.
Okay.
So yes, you're seeing the atmosphere, but I wouldn't say you're seeing the atmosphere, not the planet. I would say the atmosphere is the planet, or at least it's a big part of it.
Okay, thank you.
Thanks.
Good evening. Great talk. You mentioned that those giant solar panels will generate 500 kilowatts, which is amazing.
No, 500 watts.
500 watts. Yeah, that'd be great. Do you think that, is it possible that the very brightness of Jupiter itself might be able to work with those panels to generate some electricity?
It'll be a pretty tiny amount of electricity from Jupiter, and also, in general, the panels aren't pointing at Jupiter. We keep them pointed at the sun, and the orbit we're going to be in is kind of crosswise. So think of a spinning propeller going around the planet, always pointed at the sun, and traveling down pretty close to that dawn-dusk line where the front part of Jupiter seen from the Earth is lit up and the spacecraft's going sideways around it. So the solar panels are edge on to the planet. But in fact, the amount of light you get from Jupiter compared to the sun is pretty small.
Thank you.
So it wouldn't help much. I have cards here from people contacting us over the internet. So Beckerist asks, if it only takes a couple hours from pole to pole, how fast is Juno going? So the short answer is I don't know. The longer answer is it's about 30 kilometers a second. And an even longer answer is you really have to say how fast is it going compared to what? So if I want to compare the speed of Juno to Jupiter, I think that's the number that's in the neighborhood of 30 kilometers a second. But of course, Jupiter's moving, and the Earth is moving, and the sun is moving, and the galaxy is moving. So take your pick. For a while there, we were looking at trying to compare the speed of Juno with the launch pad on the Earth from which it launched. So the Earth's spinning and moving, and Juno's moving, and Jupiter's moving, and all of that. And we picked that because actually our PI, Scott Bolton, realized that if you pick that you got a decent case that Juno's the fastest thing ever built by people. You know, choose your reference point.
Thank you for a terrific talk. I have a question about the amount of data that you can transmit. How much can you dump, and do you have to do a lot of onboard processing of the instruments?
Okay, so for the first question, I get to say I don't know again. But actually, it's a few gigabits, not bytes, gigabits. So the entire output of the Juno spacecraft from beginning to end probably fits on my laptop, or pretty close to it anyway. And it's still a huge amount of data. But remember, we're sending it all the way from Jupiter. So you can't send it really fast. It's not like Wi-Fi here in the room. And also, the computer that flies, not only did we launch it in 2011, but we had to build it a few years before, and we had to be sure it was going to work in space in a radiation environment. So it's also, the computer is quite a bit older. Having said all of that, the most important thing we want to measure is probably the global water abundance on Jupiter, and that's one number, a few bytes.
Thanks.
With all the magnetic fields and radiation around it, it seems like a very dangerous place for a spaceship, for a probe. If someone was on a good spaceship, how close could they get to Jupiter without
if a human being was trying to survive in Jupiter, is that what you're asking?
Yeah.
Now I really don't know. I would say it's pretty hard to send a person to Jupiter because they want to ride home, and it's hard. It's hard to bring a huge rocket to Jupiter to come back. That's why we send robots, because they don't have to come home. But if you ignore all that and say how well could you survive, I don't know the answer. My guess, and it's purely a guess, would be not very long. But we'd have to go look up the numbers, and we can do that. And how much radiation you get depends not only on your trajectory, of course, where you're going with respect to the radiation belts, but how long you're going to spend there, how fast you go fly through them. That's another reason for wanting that quick 2-hour pass-through, is so that you get to spend a lot of time out far from the radiation before you do it again. And it depends on shielding it on how much energy, because different energy particles do different effects. Although I think there's a lot of things that damage people that are probably not as bad for the spacecraft. So, sorry I don't have a quantitative answer.
Well, thank you.
All right, let me look at another one of these cards. So this person doesn't have their name on it, but it says, when Juno is decommissioned and sent into Jupiter, what studies will be done during descent? So they're mentioning something that I didn't mention, but you can find on the website, which is the plan at the end of the mission is to crash the spacecraft into Jupiter. And that's to protect Europa, because Europa has a liquid water ocean. We'd like to look for life on Europa. You'd really hate to spend lots of money in 50 years and get to Europa and dig down in the ice and look in the ocean and find life, and then have to say, I don't know if it's from Europa or contamination from Juno. So we have to make sure we don't do that. It means we're going to destroy the spacecraft by crashing it into Jupiter, unless we can figure out a way to wriggle out of that. So this person is asking, what do we do? What studies will be done during the descent? The answer, we haven't settled on that yet, but the answer is probably not that much, because remember, at the end of that descent, the spacecraft's gone. And our basic model is to send the data back afterwards. We do a flyby and then we spend a long time sending the data back. So we're not going to be able to send very much information back in real time as it's falling into Jupiter. We'll be lucky if we can even maintain contact and keep the signal and tell you how fast it fell into the planet. So maybe we'll get to measure some things on that last pass as we come close, but I think by the time we're coming closer to Jupiter than the previous Para-Jove passes, we'll probably be out of radio contact anyway. Yeah.
Yeah, I have 2 or 2.5 questions about the radiometers. At what frequencies do the radiometers observe? And is each radiometer just observing one channel? And if they're observing in more than one channel, how many channels are there in a spectrometer behind each radiometer?
Okay, so each radiometer is in fact observing just one channel. And that's because what we're trying to measure, the atmosphere of Jupiter, has these big, broad frequency dependencies. So you don't gain a lot by having lots of channels, and you lose in signal to noise. That it's harder to measure with precision a lot of channels than it is to measure one big, wide channel. So there's 6 different radiometers. Each one is a different frequency. The lowest frequency, the longest wavelength, is 600 megahertz. And the next one is 1200 megahertz, which is 1.2 gigahertz. And then double it again and so forth. It's not quite exactly doubling every time, but it's pretty close to doubling from the 600 megahertz up to 20 gigahertz or so.
You said 20?
Yeah.
Yeah. And so the reason you don't have several channels in each radiometer is because the spectral lines are so pressure broadened that there's no sense in trying to resolve them.
That's right. I won't say there's no sense in trying to resolve them. I'm sure that somebody would tell me, hey, here's some great science you could do with a spectrometer. But if you're basically going after the water content, then having a lot of channels behind each of these isn't going to help you much, and it's going to hurt in signal to noise.
Hello, Greg Lancher. Will Juno be able to measure the, how shall I say, redometer and the interferometer around the equator?
Okay, I'm not 100% sure I know what you're asking. So are you asking about if we'll be able to measure the radiation around the equator, the big radiation
Well, no,
belts,
I
or
should have
the-
qualified. I was talking about convection.
Okay. So we will learn a lot about the motion in the atmosphere around the equator of Jupiter and elsewhere on Jupiter. 2 big ways to do that. One is the gravity experiment is going to tell you, when you see these big structures, it's going to tell you something about how deep they are based on the motion of the structure, the gravitational signature from it, right? So if it's moving and it's deep, you'll have a different signature than if it's moving and it's shallow, right? And then the microwave receivers, the 6 different channels, because they're seeing 6 different depths, and because they're seeing at a whole range of angles, they will also tell us something about the structure. Exactly what we're going to learn and how much we're going to learn, we're going to have to find out when we get there. I suspect every instrument has its own, every experiment has its own things to worry about. For the microwave receiver, I suspect that the biggest thing we need to worry about is that Jupiter will surprise us somehow in how the atmosphere behaves and how its temperature dependence behaves. And we'll get the measurement, but then we'll have to puzzle it out to figure out what it means. We're not there yet. Maybe I'm totally wrong and we'll get there and the models we have will be perfect. But my prediction is we'll get a great measurement and then we will eventually figure out what it means, but probably not in the first couple of days.
I had wondered if the measurements were a little bit different in regard to the meridional zones around the equator.
The measurements aren't because the radiometer just measures everything it gets, and the gravitational thing, you just measure the signature you're getting. But how to interpret them is different. As you're down near the equator and things are narrower and the dynamics going around the planet longitudinally are different, you're going to want to interpret those measurements in a different way.
Thank you.
Thank you. Let's do one more here, and then I'll read one more of these.
I don't have a question, but she has a question for you. So.
Oh, cool.
Okay. Oh.
Hi. It's too
She
hard.
asked me to ask a question.
The microphone's too high for her.
She asked
Sorry.
me like, how big is the Jupiter? I could have answered her, but she wanted to come here. But now you can answer on that.
So how big is Jupiter has lots of answers depending how you want to measure it. The simplest one is you could fit about 1,100 Earths inside it. Another way to look at it is it's 70,000 kilometers or so in radius. Another way to look at it is it weighs about 318 times the Earth. It's about 318 times the mass of the Earth. But the way I like to look at it the best is if you were coming on our solar system from far away, and you looked at the solar system and you said, what's there? And you looked hard and you found the sun, and you said, okay, I found everything. You'd be 99.5% right, because 99.5% of the mass of the solar system is the sun. And then if you looked really hard and you said, I want to find the rest of it, and you found one more thing, a little speck that's Jupiter, and you said, okay, now I found everything else, you'd be 2/3 right, because more than 2/3 of the mass of everything else is Jupiter. It's more than twice as massive as all the other planets combined. Take our whole solar system, most of it's the sun, the rest of it, more than 2/3 of it is Jupiter. So that's how big it is.
Thank you.
Let me do one more of these and then I'll take your question. So Turk182 UK asks, does that mean he's from England? That's pretty cool. Or from the United Kingdom. He says, what causes the storms on Jupiter and why are they so wild? So this time I'm not going to start with I don't know, but I'm going to end with I don't know. So the short version is the heat on Jupiter. Jupiter is hotter on the inside than it is on the outside because that heat is escaping, as I mentioned, from when it formed. And so a temperature difference drives a storm combined with the rotation of the planet. The planet's rotating really fast. You put those two things together and you get a storm. That's the short answer. The longer answer is all the reasons I don't know, because that only tells you what powers it. It doesn't tell you how that turns into a storm. Why do we get the Great Red Spot? Why do we get those belts and zones? How do they move? There are lots of people who work on the atmospheric dynamics of Jupiter and can tell you lots of things about it and how it compares to other planets such as the Earth and how it's different and details of how that works. There are people who spend their whole lives studying that. And when I look at that and look at the explanations, a lot of it boils down to, well, we know this part and we know this part and we know that part, but in the big picture to really have a full explanation, the answer is still, I don't know. It's a hard problem. We're going to get some more information about it with Juno because we'll get the depth. It's a three-dimensional thing, and we'll get that third dimension. So I hope that the answer will eventually be, okay, here's the explanation, this is how it works. But right now, the answer is still at least partly, I don't know. Okay, yeah.
Hey, I have two questions. The first one is, how do you know how old that Jupiter is the oldest planet?
All right, so the short version of that is Jupiter must have formed first, because if the other planets had formed earlier than Jupiter, you wouldn't have been able to make such a massive planet as Jupiter. Planets kind of clean up the solar system when they form, partly because the material in the initial cloud of gas and dust condenses and becomes the planet, and partly because they perturb the orbits and push things around and it spreads out away from the star. So in order to get the really big planet, it almost certainly had to form first. Right, you said you had two questions. What was the other one?
But just to follow that up, so inevitably, any other planet that would form in the solar system would have to be smaller?
I hate to agree with the word inevitably, but other than that, yeah, I think that's the general idea, at
Okay.
least, is once the big one formed, what's left over has to make smaller planets.
Right. Is it possible, does Jupiter need to have a solid core in order for the rest of it to exist, or?
It definitely doesn't have to have a solid core for the rest of it to exist. You can make models of the planet that hold together and everything without a solid core. It's the gravity that holds it together, and if you pile enough of anything, you get enough gravity to hold things together. The theorists in general say that when they work out how the planet formed, and there's lots of competing models, pretty much all the models agree there should be a dense core down in there. And notice I said dense, not solid.
Right.
We're talking about pressures that are, ridiculous, right? It's millions of times the pressure here on the Earth. We don't know how to make that kind of pressure here and hold some stuff and look at what it does. So to call it a solid or a liquid or a gas at that kind of pressure is kind of misleading. It does something, generally speaking, it's probably more like a liquid than a solid at that kind of pressure. But anyhow, it'll be much denser if it's there. There is a paper that came out, I think it's close to 2 years ago now, in which a couple of people who study that kind of thing predicted that we'll find no core at all because it will have dissolved in the liquid metallic hydrogen.
Wow,
So that'd be pretty interesting
that
too.
is interesting. Thank you.
Hi.
So I also have two questions. So if Jupiter is so massive and it formed, as at least the theory states, by several masses hitting each other and generally forming a larger mass, how did it gain so much velocity is where it spins in 10 hours?
Okay, so I want to work it backwards a little to try to explain that. It's basically, the buzzword for it is angular momentum. But imagine two ice skaters spinning around close to each other and holding onto each other, and they let go. As they spread apart, basically that rotating thing of the two of them slows down in the rotation, right? As they get further out, the rotation slows down. And that's because what's conserved is not the rotation period, but the angular momentum. The fact that you're this far away spinning is different from being this far away spinning. Okay. Now work it in reverse. Imagine the two ice skaters skating together to come and grab onto each other, and they spin around when they catch each other, right? Now we're going to turn that into lots of ice skaters, and then I'm going to turn lots of ice skaters into ice instead of ice skaters. Lots of pieces of ice coming in every which way and colliding together. They're going to make whatever they stick to is going to wind up spinning, and what direction and how fast it spins just depends on the various different random motions of all those pieces of ice that stuck together. There's going to be some leftover motion that's going to average out. Two pieces coming like this, there's velocity cancels mostly, but if they're coming at slightly, at an angle, then they're going to wind up going that way. And if you put in a third piece of ice or a fourth or a 5/millionth, you're going to get some big mess in which a lot of the motion gets canceled out and the average motion doesn't, and you wind up with something left over that's spinning.
Okay.
So in fact, I said spinning twice as fast as the Earth, it's really fast. That's true, but partly that's because the Earth spins really slow. And the Earth spins really slow for our size because of the moon, which slows down the rotation.
Okay. And also, my second question is, the first mission that went to Jupiter, where it just went straight into the atmosphere and measured the amount of water, found very little water, and you found that that couldn't be plausible based on the other experimental or at least idealized ratios. But you don't know how much water is actually on the planet. So how might that affect your theory if you don't find as much water as you expect to on the planet?
Right, so we actually wrote it on the chart here. We have 3 regions, and we had a chart a lot like this in the proposal when we first told NASA we want to do this. If you find a lot of water, it tells you, warm start, Jupiter forms close to where it is now. You find this much, the icy planetesimal thing works, and where it formed in its current location. And if you find hardly any water, like the Galileo probe reported, if that really is the global water abundant, well, this is the more complex version of I don't know, right? New planetary formation and atmospheric models needed. So far, I haven't seen anything that really explains how Jupiter forms in a self-consistent way and winds up with very, very little water. Facts trump theories. If we get there and we measure it, and that's really the global water abundance, we'll just have to somehow come up with a theory that explains it. But so far, nobody has, and they have come up with theories that explain, well, if you measure in one spot, maybe you just didn't get the global water abundance.
Thank you.
Sure. All right, I got one more card here. 604 asks, what is the chance of life on Jupiter? Well, you know what I'm going to say, right? I don't know. But I will say, if I get to narrow that question down a little bit, and interpret it not as what's the chance of life on Jupiter, but what's the chance of life like us on Jupiter? So carbon-based, water, life where, maybe it's not a person, but it's, or a mouse, but it's a creature that you would look at and would recognize as that's alive and it looks similar to the kind of life we know. On Jupiter, I'd say the chances of that are vanishingly small. And that's because the temperatures are crazy, right? It's cold at the upper atmosphere, but it gets hot pretty darn quick, and you get, there's nothing to stand on, so you fall in a little bit into Jupiter, and now you're at temperatures that are 1,000 degrees and pressures that are, thousands of times the pressure here on the Earth. Hard to picture life surviving in that. Water, there's water vapor, maybe there's water droplets if you find yourself at just the right altitude. There should be clouds and stuff, but it's not like here where there's oceans and things like that. Storms, thousands of mile-an-hour winds, all of the stuff makes it hard for me to picture life, like a puppy living on Jupiter. People would puzzle over and ultimately conclude, yeah, that's alive. Sure, I think that's plausible. Nobody's ever seen anything remotely like that, but we don't know that much about Jupiter. If you're looking for life like us, though, in the Jovian system, my favorite candidate is Europa. Europa is one of the moons of Jupiter, and it's covered with ice, but underneath the ice is a liquid water ocean. And down in the center there underneath that ocean is probably thermal vent kind of stuff and heat sources and chemistry and complex chemistry at that. And that's a good candidate for finding life. Now, I don't know if that's going to be puppies either or fish or whatever. Life took a really long time here on the Earth to go from single-celled stuff that you need a microscope to figure out it's alive to complex organisms. Things as complex, never mind us, things as complex as a cockroach have only been around for a very small fraction of the Earth's history. So my personal guess would be if we find life on Europa, it's not going to be fish, it's going to be microbes. That would still be really exciting. It would teach you a lot about how life formed and where it comes from, and does the life there look like life here, or did it form in two separate ways? And here on the Earth, one of the theories for how life began is thermal vents at the bottom of the ocean. So if you find it in Europa and you get to do comparisons, that would be amazing. So I'd be really excited about it, but I'm not counting on puppies or fish in Europa either. Okay.
Hi, so I only have the one question. Based off of the quick time that you had with the 36 paths that your Juno was going to do, It looked like it was going a little closer to the northern pole than the southern pole
Yes.
on each flyby. And what was the choice behind that? Why not go south to north? Is
That
there
was the
just
orbit
more
we could
interesting
get.
stuff?
So remember, I'm showing it again so other people can see what you caught, because you probably caught it quicker than most people. When you look at this, what's going on here is each time it goes past Jupiter, because Jupiter's not a perfect sphere, the orbit gets twisted around a little bit. What's called the line of Apsides, which is just the direction of the long axis of the orbit, gets shifted from horizontal down. If we had come in a slightly different orbit, it could have gotten shifted up instead of down, but the orbit that worked the best and so forth winds up with us going a little bit over the northern pole and having it stretch further and further down in the south.
But was there any reason to have it go north to south instead of south to north?
Not really, no.
Oh, okay.
Just the way it came out.
Thank you very much.
Sure.
Hi, he has a question.
How far is Juno far to Jupiter?
Okay. So,
Oh, in miles, please.
all right, let's see. So, I don't, Earth and Jupiter both move, and I don't happen to know exactly where they are right at this moment, but roughly speaking, it's about 500 million miles to Jupiter. And I don't know exactly, because the spacecraft is moving and I haven't looked it up lately, but it's in the neighborhood of 100 million miles from the spacecraft to Jupiter. It's probably a little less than that. And you can find out the exact answer from that Eyes on the Solar System website. It's a really cool site, too. So you go to the website, it shows you pictures of the different spacecraft and how they're orbiting and where they go, and you can play with the time and say where they were before and where they are now. You might need help from your mom to get it up and going. I don't know how expert you are with computers, but it's not a hard website to use, and it's got all kinds of cool stuff, including every day you can get the latest numbers for how far away it is and how close to Jupiter it is. Sure. You're welcome.
Hi. So thanks for your talk. It's really great. I was wondering, so if there was life on Europa, could that have had any difficulties associated with the intense magnetosphere on Jupiter?
Right. So if there's life on Europa, would the radiation belts destroy it, right?
Mm-hmm.
And maybe. Radiation environment at Europa is hotter than here on the Earth, but we're protected by an atmosphere, and Europa is protected by ice and an ocean. So I would think if you're down at the bottom of the ocean, radiation out there in space is no big deal.
Okay.
If you're on the surface of the ice, you're probably getting bombarded. So it's another reason to look for life in the ocean rather than on the surface. And I should say, there's I forget what stage they're officially in, but there's a project or a pre-project to send a mission to Europa that people have been working on for quite a while to look. It's multiple stages. We're not ready to, go dig beneath the ice right away, but there's a lot of cool stuff to be learned about Europa, and there's people here at JPL, for all I know, in the audience who can tell us a lot more about life on Europa than I can.
Thanks.
Sure. So that's my wife, Lisa, and
Hi,
my son,
Dr.
Brian.
Levin. We wanted to know, when Juno gets to Jupiter, how busy will the team members be? And in particular, how busy will you be?
So the answer is very, very, very busy. Remember I said every 2 weeks, don't think of it as an orbit, think of it as a flyby every 2 weeks. So picture the chaos and pandemonium you see when there's a flyby of one of the planets or moons and everybody's working to try and make sure you get every last little bit of data out of it and that you fly the spacecraft without breaking things and all of that stuff. And now we're going to do that every 2 weeks for a year and a half. So yes, really, really busy, but I promise, Brian, we'll still have time to play pool once in a while.
I was wondering what the mission team members are going to be doing when it gets there.
Oh, what are all the, well, we have a lot of people on the team and they do lots of different things. So each of the instruments has a team of scientists and engineers who work with that instrument for the measurement they're doing to try to understand the data, to try to understand what it means for what they should measure the next time around, to try to send commands up to it and tell the instrument what to do, and to make sure that you're doing all that in a way that's safe or you're not going to break anything. And then there's a team of people who take all those inputs from all the instruments and all the corresponding inputs from the spacecraft for running the spacecraft itself, and put all that together and try to make sure that that sequence of commands that you tell the spacecraft what to do is doing the right things and isn't going to break anything, and has been properly checked and tested. And that has to get sent up to the spacecraft, and there's people who work on that. There's system engineers who are basically the people who take a step back and look at the entire system and make sure that everything's working and playing nice together and everybody's writing down what they're doing and following the right procedures. And even though we're tired and we've been at this for a year and doing it every 2 weeks for a year, and it's the middle of the night, that you're still not making a mistake, right? And there's a mission assurance team of people, especially a key person, the mission assurance manager, who looks over all of that to make sure we're doing everything right and safe. And if we do have problems, that we're working on understanding them and not just saying, oh, never mind, and moving on, and then something breaks later. Well, in all seriousness, if you're working on a big complex problem and something comes up and you don't quite exactly understand it, but it works and you get to move on, there's a strong temptation to say, I'm not quite exactly sure what happened there, but it's probably okay, and I'm busy over here. It's really hard to have the right frame of mind to say, I don't understand that, there's potential safety implications, we need to spin up a big team of people and make everybody work on that. Mission assurance is the team, is the people who keep the cool head and say, I know you're busy, but we need to take care of this. This has potential implications, we have to work at it. So it's good to have separate people who do things like that. And lots more. There's I won't try to list everybody who works on the spacecraft and the team, but they say it takes a village to raise a child. Well, the spacecraft is my 4th child, the one in space, and it takes a lot more than a village to make it work. Yeah.
Hi. So it's said that Jupiter is our protector. It protects us from all the flyby objects and stuff. So
I didn't say that, but it's true.
Yeah. So since it's gaseous, so when something hits, it just gets absorbed really quickly, right? So since it's spinning, do we know when things hit Jupiter that it has protected us at any moment in time?
So first I should make clear that Jupiter doesn't protect us just by things hitting the planet. It's got this huge gravitational field. It's huge, right? And its gravity tends to change the orbit of things that come by. And it turns out that as objects from the outer solar system that could potentially hit the Earth, say, if Jupiter wasn't there, as they go by, they're more likely to get pushed out away from the Earth than they are to get pushed in towards the Earth. So that's the sense in which it protects us. But that question about if something hit it, would we even know, is a really good one. The answer is, yeah, lots of things could be hitting Jupiter that we would miss. Depends how big it is and whether anybody was looking at the time and things like that. A comet hit Jupiter some years ago that was really interesting, and the whole world studied it. And it led to the question of, hey, how many times has a comet hit Jupiter and nobody noticed? And we didn't really have a solid answer for that. There's more people looking now because that was such an interesting thing. But it leads us to another reason why Jupiter's a great place to study if you're trying to learn about how planets formed in the early history of the solar system. Because it's so big, impacts like that have less of an effect on Jupiter than, say, the Earth. If the Earth got hit by something asteroid-sized, say, 1 billion years ago, there'd be a huge change in what you see here on the Earth. And if you tried to figure out what happened before it got hit, that would be difficult. Now, we don't think it got hit by an asteroid-sized object. Well, maybe a small one. If Jupiter got hit by something that big, you'd see it, but it wouldn't make a huge change in Jupiter because Jupiter is just that much bigger. So it's another reason why you're learning more about the early history when you look at Jupiter. Small stuff doesn't change it. Jupiter doesn't sweat the small stuff.
Thank you.
Okay, we need to stop soon. So let's make this the last question, and then if anybody wants to come up and talk to me, afterwards, we can do that too.
Real quick, I missed the start of your lecture, so you may have talked about this. One is, why didn't you use RTGs to power the spacecraft?
So why didn't we use RTG,
Instead
nuclear
of the
power,
solar, right.
to power the spacecraft instead of solar power? Basically, we used solar power because we could. Not every mission can do that. I mean, we're only running on 500 watts, but when we looked at what we could do and what we wanted to do at Jupiter, it fit within what we thought we could get out of solar panels. And at the time, remember quite a while ago, that we were doing the initial proposals and studies and designing the mission, it wasn't so clear that RTGs, the radioisotope thermal generators, would be available on the timeline that we needed for the mission. So it wasn't just we can make solar power work, it was also we think solar power is a better decision than nuclear. Some other mission doing some other thing, is going to make a different
most
decision.
of your deep space missions don't use.
Right.
Okay, next part of that is, what did you do to shield the electronics in the spacecraft?
Oh yeah, I didn't mention the vault. If you go to our website, there's a whole stuff about it. Basically, we put as much of the electronics as we could in this giant titanium box. So a whole lot of mass, just big metal box to protect it from the radiation. And we believe that the radiation environment inside the vault, the radiation vault, is not much different from the radiation environment at, say, Mars. Outside the vault, it's a lot worse, but we knew, we've sent stuff to Mars, we've sent stuff to other planets. We wanted to bring as much of the electronics as we could into a realm where we already know how to make that work. And so we put it in this giant vault, it's like a tank. It's like sending a tank to Jupiter with all your electronics inside it.
Okay, great, thank you.
All right, thank you.